You flip a switch, charge your phone, make some toast. We're using electricity all day, every day. And let's be honest, for most of us, it might as well be magic. But it's not. Today, we're going to pull back the curtain on what's really happening inside all those wires. It's simpler and, frankly, a lot weirder than you might think. So let's dive in. We all see these huge power grids and know, okay, that's where the power comes from. But what is that power, really? What is physically moving through the wires to make your lamp turn on the very instant you hit the switch? That's the big question we're going to answer. Okay, so to wrap our heads around this, we're going to start with a really classic analogy because it works surprisingly well. I want you to imagine that electricity isn't some invisible, mysterious force. Instead, just picture it as an invisible river flowing through your walls. All right, look at this. On the left, you've got something we all get, water flowing through a pipe. Simple enough. Now, look over at the right. It's pretty much the same thing. Instead of water molecules, we have tiny little things with electric charge, and the pipe is now a wire. But the core idea, something flowing through a tube, it's exactly the same. This chart breaks it down perfectly. So what's actually flowing? For water, it's water molecules. For electricity, it's electrons. Now, what about the push that gets it all moving? With water, it's pressure. With electricity, we call that voltage. And the flow itself, we call it a flow rate for water, but for electricity, we simply call it current. It really is that simple. More voltage gives you a stronger push, which gives you more current. So that water analogy is a great starting point, but this is where things start to get a little strange. The reality of what those tiny electrons are actually doing is much more chaotic and, honestly, way more interesting than a simple, smooth river. Let me ask you something. When you flip a light switch, the light comes on instantly, right? It feels like it's happening at the speed of light. So it makes sense that the little electrons carrying that signal must be just zipping through the wire at light speed too, right? Well, get ready for a surprise. Look at the diagram on the left, labeled A. That's what the electrons inside a copper wire are doing right now, just bouncing around completely at random, like a chaotic swarm of bees. But the moment we apply that voltage, that push, it creates an invisible electric field through the wire. And as you see in B, that field gives all those chaotic electrons just a tiny collective nudge in the same direction. We call this slow, shuffling motion drift velocity. And just how fast is that drift? Check this out. Less than 1/4 of a millimeter per second. That is unbelievably slow. An electron would take hours, literally hours, to travel just 1 meter. So here's the mind-blowing part. The electric field, the signal that tells the electrons to start moving, travels at nearly the speed of light. But the electrons themselves are just shuffling along. It's exactly like doing the wave in a stadium. The wave itself zips around the stadium in seconds, but each person just stands up and sits back down in their seat. I love this quote because it just sums it up perfectly. It's not a high-speed race. It's a colossal, slow-motion shuffle. The electricity we use is this massive, coordinated movement of trillions of particles, all nudging each other forward at the same time. Okay, so we've got this giant crowd of electrons shuffling along. But here's the thing. A wire isn't an empty hallway. It's packed with atoms. So for the electrons, moving through it is like trying to push your way through a super dense crowd. They're constantly bumping and jostling and running into things, which creates a kind of electrical friction. And in the world of electricity, we have a name for that opposition. We call it resistance. It's just a way to measure how much a material fights back against that flow of current. The unit we use to measure it is called the ohm. This diagram really brings it all together. You start with a potential difference. That's just the official term for our voltage, the push. That push creates the electric field inside the wire, and that field gets the current flowing. Resistance is simply the property that connects the push to the flow. It's what determines how much current you get for a certain amount of push. Yeah, think of it this way. A material with really high resistance, you have to push incredibly hard just to get a tiny little trickle of current to flow. But with a low resistance material, that exact same push can result in a massive gush of current. It's all about how much the material decides to fight back. So this idea of resistance isn't just some random physics thing. Oh no. It's something that engineers use very, very intentionally to control exactly how electricity behaves. It's a key ingredient in pretty much all of our electronics. Okay, look at any circuit board, like this one. You see that tiny little component with the colored stripes? That's a resistor. Its only job in life is to add a very specific, calculated amount of resistance to the circuit to basically act as a speed bump for the current going to other, more sensitive parts.
So how do you know how much resistance it has? I mean, there's no tiny print on it. Instead, they use a secret code, these colored bands. It's a universal language for electronics. Each color stands for a number or a multiplier, so you can know its exact value just by looking at it.
Let's crack the code for that resistor we just saw. The first band is yellow, that's a 4. The second is violet, that's a 7. Put them together, you get 47. The third band, black, is the multiplier. In this case, just times 1. And boom, the value is exactly 47 ohms. How cool is that? Okay, we've got the slow shuffle of electrons. We've got the resistance that gets in their way. Now let's put it all together to explain something you probably see every single morning.
But wait a second, this seems completely backward, doesn't it? If the whole point is to get current to flow and power our stuff, why on earth would we ever want to intentionally oppose it with resistance?
It's because that opposition, that struggle, is actually incredibly useful. Think about it. Rub your hands together really fast. They get warm, right? That's from friction. Well, it's the exact same idea here. As all those electrons struggle to push their way through a resistant material, that electrical friction generates a ton of energy. And that energy has to go somewhere, so it gets released as heat, and if it gets hot enough, as light. And here's the key. Every material has its own natural, built-in property for this, and it's called resistivity. Just look at this chart. Way up at the top, you have materials like silver and copper. Their resistivity numbers are tiny. They're basically super highways for electrons. But then look down at something like nichrome. Whoa, that number is way, way higher. It's designed to be a traffic jam. And this brings us right back to your toaster. The cord that plugs into the wall, it's made of copper. Super low resistivity. We want the power to get to the toaster easily, with no fuss. But the glowing wires inside the toaster, that's nichrome. We choose that material specifically because it has high resistance. It fights the current, gets incredibly hot, and toast your bread. It's absolute genius. So let's just quickly recap what we figured out. We've seen that the electric current in your walls is not a lightning-fast race, but a powerful, slow-motion shuffle of electrons. We learned that this shuffle runs into an electrical friction we call resistance. And most importantly, we've seen how we can engineer this friction using low-resistance copper for wires and high-resistance materials for toasters to control electricity and make it do all sorts of useful work. It's a beautiful interplay of forces that powers our entire modern world. So the next time you flip a switch, you'll know it's not one little electron racing all the way down the wire. It's a signal that instantly starts this huge, powerful shuffle right there inside the wire by your hand. Kind of makes you wonder, doesn't it? What other simple electrical things that we do every day are hiding some really fascinating physics right below the surface?